Math 111 OLC Winter 2012. We're going to start Unit 4, and we're going to start Chapter 4 today in our text. We're going to begin with Section 4.1, which is entitled Solving Linear Inequalities. Alright, I think the techniques of solving equations will be brought to remembrance when we are asked to solve inequality statements. A lot of the mechanics are the same. Some things are different though. So let's start out nice and easy with an inequality of this type. Alright, we're really saying here we want all the x values that solve the statement 6x minus 27 is less than 9. Not equals 9, less than 9. And again, it's somewhat similar to solving equalities, where we want to do algebra things to both sides of the inequality statement in order to isolate the x variable on one side and get a number on the other, thus describing a solution set. Alright, so what I'm going to do here is, well, to isolate x on one side of the inequality, first thing I would do is subtract 27 from both sides. Now, you'll recall when we add or subtract anything from an inequality statement on both sides, we leave the arrow alone. All right, the arrow is not affected, and you'll get an equivalent inequality statement. All right, so if I do that here, I get 6x. I'm sorry, I want to add 27 to both sides. Excuse me. All right. I want to add 27 to both sides. Let me check that. Okay. So I get then this statement, 6x is less than 36. And that's an equivalent statement. Now I'm going to divide both sides by positive 6. And let me make a note here. When you multiply or divide an inequality through by a positive quantity, that didn't quite come out right. Hang on a minute. When I multiply or divide an inequality through by a positive quantity, and here 6 is positive, I leave the arrow alone. Alright, so I'll leave the arrow alone, and I get then the equivalent inequality statement, simplifying on both sides, x is less than 6. Okay? This I call my solution set for the inequality statement. This tells me all values of x that are less than 6 will solve the above statement. I can easily graph that solution set on the number line, and typically that's what we'll ask you to do in these homework problem type statements, is solve and graph the solution set. Well, less than in terms of number line means left of. So I'll draw an open circle here denoting an open set. Right, this tells me the value of 6 is not included in this solution set. 6 we often call the boundary value. So I'll shade in all numbers left of. The left of means less than. All the way down to negative infinity. Right, to give you a suitable graph of my solution set for this above inequality. So there's my solution set and a simple inequality statement and my number line graph of my solution set. Let me make a note about the answers in the back of the book to problems of this type. Our author uses an alternative notation for this idea of an open circle, and what the author does, or authors do, is something like this. They put a parentheses at the boundary value to indicate the boundary value is not included. So if you're wondering where the answers in the back of the book come from, their graphs don't look quite like our graphs. This is why. I think most students are more comfortable with this open circle notation than they are with this parentheses notation, and I suppose we should be able to handle it either way. Let's do another example. Solve and graph solution set. Nice and easy. Let's start out. Start small and build up big. Alright, same idea. I'm going to want to do algebra things to both sides of the inequality statement in order to isolate the variable on one side and a number on the other. Alright, I would probably subtract 4 from both sides, and again, when you add or subtract an inequality through by anything, leave the arrow alone. Alright, so I get the equivalent inequality, 8x is greater than minus 40. Alright, I would now want to divide both sides by positive 8. And notice, when you multiply or divide by a positive, and 8 is positive, we leave the arrow alone. Okay? So I get x all alone on the left is greater than minus 5 on the right. So there is my solution set. This tells me all x values greater than minus 5 solve the inequality statement. And I'll graph the solution set. I usually like to put 0, demarcate 0 on these number line graphs, make sure I'm on the correct side of 0. Minus 5 I'll indicate down here somewhere. Again, this is an open set, a strict inequality. Right? The boundary value of minus 5 is not included in the set. I indicate that with an open circle and shade in all numbers to the right. Of course, our author would probably draw something like this. A parentheses at the boundary value indicating the boundary value is not included. Okay? Show another one. Solve and graph solution set. This one's a little nastier, but not much. Alright, the rub here is you've got more terms than we saw in the first two examples on each side of the inequality statement. However, the goal is the same. Get the variable on one side of the inequality statement. And notice here we've got a less than or equal to. And that symbol, that little bar there below the less than sign, means just what you think it means. Less than or equal to, meaning the boundary value will be included in our final solution set. Alright, clearly I can combine some like terms here on each side before I start crossing over the inequality symbol. So I'll write on the left minus 4x plus 4, and on the right 1 minus 15 becomes minus 14. So I always like to clean things up within sides before I start crossing over the inequality symbol. Alright, I would probably subtract 2x from both sides, and if you're going to do that, you'd probably subtract 4 from both sides. And again, when you add or subtract, leave the arrow alone. It doesn't matter what you're adding or subtracting to or from. Alright, I end up with a minus 6x on the left is less than or equal to minus 18 on the right. Alright, now here's where things get a little different than solving inequalities. I'm going to want to divide both sides by negative 6 to clean up and get an x variable on the left. But when you multiply or divide an inequality through by a negative quantity, and here we're dividing by negative 6, you got to reverse the inequality arrow direction. So I usually indicate that with a little squiggly arrow like that. It's an easy step to forget. So I then get the simplified statement x is greater than or equal to 3. There is my solution set. This tells me I want all numbers greater than 3, and in terms of number line that means to the right of 3. So let me draw a quick graph. 0 somewhere in the middle. I'll put 3 on the right hand side of 0. Right now, this greater than or equal to, it means just what you think it means. It means the value of 3 will be in my solution set. So I denocate or demark that with a closed circle. So anytime you see a equality statement included in the inequality, you'll want to note that with a closed circle. And I shade in all values right of 3. Greater than 3 means right of 3 in terms of number line. And there is my solution set graph. Our author denotes this a little differently as well. What they do is they put brackets to indicate a closed set. They indicate that with a bracket instead of a parentheses that you would see in the open set. So we're still at positive 3 here at the boundary. So either way, and I think most of us would be more comfortable with a closed circle. If you want to use the author's bracket notation, that's fine. Okay? All right, let's do some tougher ones. Solve and graph solution set. That's my little time-saving acronym. I'll say 7 is greater than 10⁹ s plus 2. Alright, this one's copied out of the book somewhere. Alright, so we've got some unpleasant fractions here to deal with. We've got a fractional multiplier in front of our variable, and of course we want to get rid of the fraction. Alright, first thing I would do is multiply both sides, all terms, by positive 9. And again, when you multiply or divide by a positive, you leave the arrow. Alright, so I'll leave the arrow and I'll say get 63 on the right. 9 times 10⁹ s is 10s. I got to apply my distributive law. And 9 times 2 is 18. So I get the equivalent inequality. 63 is greater than 10s plus 18 with no fractional multipliers on my variable. Alright, I would probably subtract 18 from both sides. And 63 minus 18, let's see, 63, 53, 43, 45, right? 45 on the left is greater than 10s on the right. And again, when you add or subtract by anything, and an inequality through by anything, you leave the arrow alone. Alright. Now what do we want to do? Well, of course, we're going to divide both sides by 10. By that I mean positive 10. We're going to divide both sides by positive 10. Of course, positive 10 is positive. So we leave the arrow alone. 45/10. Well, 5 goes into both of those. 45/10 reduces to 9/2. And on the right, we've got 10s over 10 is just positive s. Alright, now some students have trouble reading this inequality statement. All right, there is my solution set, and I claim that's a fine statement of your solution set. Well, what does this mean? It means 9/2 is greater than s. Could I also read this right to left? And this is equivalently s is less than 9/2. Write that down. 9/2 is greater. Hang on a minute. Nine halves is greater than s. That is equivalent to the statement s is less than 9/2. And of course, less than means left of. Alright, so we should be able to read these inequality statements left to right or right to left as needed. Well, if s is less than 9/2, that means I want all numbers on the number line to the left of positive 9/2. So I'll denote 9/2 somewhere right of 0. Less than means left of. And again, I'm going to draw an open circle here. A strict inequality means an open set, boundary value not included. And there is the graph of my solution set. All right, so here is my solution set. And either way, you could either write it like this or like this. They're both equivalent. And of course, this is the graph of my solution set. Okay? All right, let me get a fresh screen here. All right, let's see. Let's get something a little nastier here. Solve and graph solution set. Let's start out something like this. All right, 3 halves times x plus 2 is less than or equal to 3 fifths times x minus 3. That's a 3 there. Okay. Alright, so again, I'm going to want to do algebra things to both sides of the inequality statement to isolate x on one side, get a number on the other. And, well, I've got to be careful. When I multiply or divide through by a negative, you've got to reverse the arrow. Well, we're not there yet. Let's see. I want to get rid of the fractions. First step, I'm going to multiply both sides by positive 10. All right, now multiply. This is already a product on the left and on the right, so I can apply my associative law of multiplication. And I'm going to multiply 10 times 3 halves first. 2 goes into 10 5 times, and 5 times 3 is 15. And then I'll multiply by x plus 2 in my next step, okay? Similarly, on the right-hand side, I want to get rid of this fraction first. 5 goes into 10 twice. 2 times 3 is 6. 6 times the remaining factor, x minus 3. Okay? Alright. So, now, again, I leave the arrow alone. Let me make a note of that. I multiply. When you multiply or divide by a positive, leave the arrow. Alright, now I'm going to want to free up these variables in terms for combining. So no choice but to multiply, perform the indicated multiplications on the left and right. I'm not crossing over any symbols there, any inequality symbols there, so I can perform those independently. And let's see. I'm then going to want to subtract 6x from both sides, right? And if I do that, I'd probably subtract 30 from both sides. All right, well, 15x minus 6x, that's going to be a 9x on the left. 30s cancel out on the right, on the left. On the right, the 6x's cancel out, and I'm left with minus 48 on the right. So 9x is less than or equal to minus 48. Of course, I want to solve for x, so I'll divide both sides by positive 9. And again, when you multiply or divide an inequality through by a positive quantity, you leave the arrow. We're dividing by a positive 9. So I get x on the left is less than or equal to, well, let's see, minus 48 over 9. 3 goes into both of those, right? So I'll reduce this to minus 16 thirds. Okay? That's negative 16 thirds. And that's an improper fraction, a simplified improper fraction, so I'll say that's fine. And there is my solution set. X is less than minus 16 thirds. And if I ask for a number line graph, again, less than means left of. Negative 16 thirds is negative, right? Somewhere in the neighborhood of negative 5. I'll just plot a point somewhere left of 0, indicating my boundary value of minus 16 thirds. And again, less than means left of. Less than or equal to indicates a set closure at the boundary, and of course all values to the left all the way down to negative infinity. Okay, and again our author would use this graph notation to indicate set closure. You can use one or the other. Okay, alright, let's see, let's do a couple more in this vein with some fractions to deal with. Solve and graph solution set is my time-saving acronym. 1/2 x plus 6 is greater than or equal to 4 plus 2x. Alright, I want to find all the x values to turn this inequality into a true statement. Of course, I want to get rid of the fraction, and I can do that easily by multiplying both sides by positive 2. I leave the arrow alone because I'm multiplying by a positive. Well, you've got to apply your distributive law on both sides. 2 times 1/2 x is x. 2 times 6 is 12 on the left, greater than 2 times 4 is 8, plus 2 times 2x is 4x on the right. Alright, I would probably subtract 4x from both sides, getting my variable on the left-hand side, and if I'm going to do that, I would probably subtract 12 from both sides. And I'll get minus 3x on the left is greater than or equal to minus 4 on the right. And I'm going to divide both sides by negative 3. And I need to reverse the arrow because I'm dividing by a negative quantity, right? Alright, so I get a simplified statement. X is less than or equal to positive 4/3. Again, negative 4 over negative 3 reduces to positive 4/3. And here is my solution set. All x values less than 4/3, less than or equal to 4/3, will solve this inequality. Alright, 4/3 is a little bit bigger than 1. I'll just put a positive number somewhere right of 0 to indicate my boundary value of 4/3. Equality is included in the solution set statement, so I need a closed circle here. And less than means left of. All the way down to negative infinity. Again, the author would indicate this with a square bracket at the boundary value. Either way is fine. Alright, let's try one more. And this one pretty much represents the upper limit of difficulty for this section. 4.1, solve and graph solution set. Alright, so I've got all kinds of things happening here. I've got fractional multipliers. Within those products, I've got nested statements, nested subtractions and additions. A lot going on in this problem. First thing I want to do is get rid of these fractions. Don't deal with the fractions if you don't have to. If I multiply both sides by the magic number, all these fractions will go away, and the magic number here is 9, right? 9 is the LCM, the LCM, the least common multiple of 9 and 3. That's 9. So I'm going to multiply both sides, all terms, by positive 9, and I leave the arrow alone. 9 times 5 9s. I'm going to multiply that product first because the 9s cancel out, and 9 times 5 9s is 5 times the remaining expression, x plus 3. Minus, again, we're applying my distributive law here, 9 times 4/3. Well, 3 goes in the cross, cancels into 9 3 times, and 3 times 4 is 12. 9 times 4 is 12 times 3 is 9 times 4 is 24. 24 times 3 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 is 24. 24 times x minus 3, the remaining expression, is then less than or equal to 9x minus 9 on the right. Looks better already. 5x plus 15 then minus 12x plus 36 is less than or equal to 9x minus 9. Alright, I want to combine some like terms here. The x terms will combine as minus 7x. 15 and 36 are 51. Can't do much on the right without crossing over the inequality statement. So now I'm going to do some surgery on both sides. I'll subtract minus 9x from both sides. And if I'm going to do that, I would subtract 51 from both sides. And I'll get a minus 16x on the left is less than or equal to negative 60 on the right. And notice I have not changed the arrow. If I look at my original equation, in all this work I did not multiply or divide by a negative, at least not yet. Alright, now I'm going to divide both sides by negative 16 to solve for x, right? And now I reverse the arrow. Let me simplify now both sides. Minus 16x over minus 16, I get x on the left. And negative 60 over 16, well, negative over negative is positive, and 4 goes into both. 4 goes into 60 15 times, and 4 goes into 16 4 times. So there's a reduced, improper but reduced fraction on the right-hand side, and I claim this is my solution set for the above inequality statement. And I can get a graph very easily. Well, 15/4, of course, is a positive number, somewhere in the neighborhood of 4. So I'll just denote my boundary value of 15/4, somewhere right of 0 on the number line. Equality is included in this inequality statement, meaning my closure, my boundary value is included. Set closure, they sometimes call that. Closed set. And everything to the right, off to positive infinity. Make a nice big fat arrow, is included in this solution set. So there's the solution set, and here's my solution set graph. Okay. Alright, we'll call it a day. Homework, of course, is listed in the Unit 4 folder. And this concludes lecture on Section 4.1, Math 111 OLC Winter Session 2012. That is all.